Finding the least common denominator of rational expressions using number theory. Finding the least common denominator of a rational expression may be a task that we need to complete when solving rational equations or adding and subtracting rational expressions. And for some, that can be a difficult task. So I want to give you a nice equation from number theory that will make finding the least common denominator easier. That idea is the following. If we have two things, say A and B, and we find their product, that should be equal to the GCF of A and B times the LCM of A and B. Now, the least common denominator of rational expressions is also the least common multiple of the polynomials that represent the denominators in those expressions. So before we take this equation and manipulate it in a way that's going to be of use to us when finding the LCM, let's just first show how this works. So I'm going to choose numerical examples for A and B to start. So let's say A is 25 and B is 15. If we find their product, we'll get 375. Now, based on this equation, it should be true that the product of A and B should equal the GCF times the LCM. So what's the GCF of 25 and 15? Well, the greatest common factor, or the largest number that goes into both 25 and 15 evenly, is 5. The LCM, the smallest number that both 25 and 15 go into evenly, is 75. And when you multiply 5 and 75, you do indeed get 375. So I know this is not a formal proof of this fact, but showing this numerical example is showing you how this works. So now, why is this nice to use when finding an LCM? Well, we just have an equation here. So what we're going to do is we're going to divide both sides by the GCF. And now we have an equation for an LCM between two things. So the LCM should be equal to the product of those two things divided by the GCF. And the reason why I'm presenting this in this video is because what I found with students is they have a good understanding and are competent when multiplying polynomials, which is how we're going to find A and B. And then finding GCFs between polynomials is also something I found students do very well with. And when we divide those two things, that now turns into a simplifying rational expressions problem, which is another task that I found students have a lot of success with, the idea of just canceling things from a factored format. And as a result of those three things, we'll get our LCM. Now, it must be noted that this equation is true for two things, right? So A and B. So what if we have three different denominators or three rational expressions, or I should just say more than two? What you want to do is if you have A, B, and C that you're looking at, and you want to find an LCM amongst those, and you still want to use this number theory part, choose two. So say we'll work with A and B, we find the LCM. Then we're going to call that LCM, we'll just rename it A prime. And let's call this our B prime. And now what we're doing is finding the LCM between these. Okay, so before we just dealt with A and B, so let's call the LCM of A and B A prime. We'll rename C B prime, and now we're trying to find the LCM. So we really have this kind of like nested problem where we just keep extending down. We're only ever working with two because that equation that we started this video with supports two things. So if we have D, we'll call this A LCM between A prime B prime being C, call that A double prime. We drag down C, call that B double prime, and we find the LCM between those two. And that LCM at the final product would get you the LCM between A, B, C, and D, okay? So we're only ever working with two at a time. Find the LCM between two, use that to find the LCM with the third or the fourth, and so on and so forth. So let's jump into some examples. We're not looking at rational expressions specifically right now, but just some standalone polynomials to kind of get used to how the equation works. So imagine that these would represent your denominators in rational expressions, and we're trying to find that LCM between them. So before we even start, because we're going to ultimately be simplifying a rational expression in the end, we want to have factored format. So the first one, x plus 2 squared, is already factored for us. this quadratic trinomial can be factored into x plus 3 times x plus 2. So the first thing we're going to do is find the product, because what we've learned is the LCM is equal to the product divided by the GCF between two expressions. So the product, when we multiply these together, x plus 2 cubed times x plus 3. And notice how I'm leaving the product in a factored format. I'm not expanding out these polynomials because, once again, we ultimately want to simplify a rational expression in the end, which would require me to refactor it. So I don't want to waste any time doing some unnecessary steps. So now GCF, what's common amongst the two terms? X plus 2. So now we can find the LCM, being the product divided by the GCF. We now have a simplifying rational expressions problem where we get a cancellation, x plus 2 squared times x plus 3. And that would be your least common denominator if these were to represent denominators in rational expressions. Now let's take a look at some monomial terms. So product, these don't have to be factored. We're multiplying 40, and then using exponent rules, adding exponents, x to the 4th, y to the 7th, z. GCF, amongst the numbers, be 2. Amongst the x variables, just x. Amongst the y squared, and z is not shared, so it's not included in the GCF. It's not a common factor. So our LCM, 40x to the 4th, y to the 7th, z over 2 xy squared. And now we'll make a simplification. 40 divided by 2 gets us 20. Y to the 4th over x, x to the 4th over x. Subtracting exponents now. X to the 3rd. For the y's, we'll get y to the 5th. And there's no z to cancel with the numerator z value in the denominator. So here is our LCM, doubling as our least common denominator had these monomial expressions been denominators in rational expressions. Now, another example, but this time we have 3. So going back to what we started with, how do we handle 3? We're going to be working with 2, and then finding the LCM of that, and using that LCM as our new value to compare with the third to find the LCM amongst all of them. So factored forms, I'm going to take out a GCF from the first, x squared minus 9 is left behind. Difference of squares, x plus 3, x minus 3. Take out an x here. We're going to have quadratic trinomial to factor x minus 5, x plus 3. So I'm just working with these first two right now. Product, x squared, x plus 3 squared, x minus 3, x minus 5. GCF, what's shared? X and x plus 3. LCM, if we were to write the product over the GCF, you would notice x's would cancel and x plus 3's would cancel, and we'd have x, x plus 3, x minus 3, x minus 5. So this is the new thing we want to work with compared to this, which is going to factor into x, x plus 3. And now we're trying to find the LCM between these in order to get the LCM between the original 3 expressions. Think of this being my A, my B, and my C. So how do we do that? Well, once again, we find the product. And when we multiply them, x squared, x plus 3 squared, x minus 3, x minus 5. The GCF is x, x plus 3. So same as the first one, it just so happens to be in this problem. So our LCM amongst all 3 would be, after some cancellations, x, x plus 3, x minus 3, x minus 5. And to finish off the video, now you see rational expressions that need to be added together. They have uncommon denominators, so we want common denominators, which we've now learned is the LCM of the denominators. How do we find it? If we use the number theory idea, fully factor to start, difference of squares. Here, we find the product we find the GCF. Now we can find the LCM, which doubles as our least common denominator. You'll notice that the x minus 2's would cancel, x minus 2, x plus 2, x minus 3. So we need to adjust these denominators accordingly. This would need an x minus 3, and the top would need to be adjusted in the same way. This would need an x plus 2. The top would need to be adjusted in the same way. So that's how we can use number theory to find our least common denominators of rational expressions, using only two denominators at a time. Find the product, find the GCF, write the LCM as the product divided by the GCF, simplify that rational expression, and you have just found the least common multiple between those polynomials or monomial terms. And that concludes the video.